All right, let's go ahead. I'll get started here. Start talking. Got a lot of stuff to talk about today. So this week we're talking about what are we talking about? Total station instruments, measuring angles. Chapter 8 is chapter 9 in our elementary land surveying book. I've kind of got a little uh, slide presentation for chapter 8 and chapter 9 I'd like to try to run through. And as you can see, I've tried to dress it up, add some color. I even put some pictures in it. So it's like trying to dress up my world famous boring PowerPoints. So chapter 8 talks about total station instruments, angle observations. Oh, look at that. We even got some. Did I do it right? Maybe. Oh, oh, oh. Go back, go back. Oh, wait. Okay, I don't like that. So the topics included this: total station characteristics, instrument components, instrument setup, angle measurement methods, error control, and angle observations. Hopefully, the learning objectives after this lecture, you should be able to identify major components of a total station, explain how total stations measure angles, properly set up and level a total station. We'll actually get into that on the lab, and describe methods for measuring horizontal angles, understand angle measurement accuracy, and error control. And note to self, I'm going to take out animations because it jumps too fast. I don't like that. So way back when survey instruments, early instruments were the compass, which you see up there on the top left picture. Surveyors would set this up, usually on a single staff, or it could be a tripod. These veins that stick out on the side is what they would sight, the line that they were observing. The compass in the middle, they would take a direct bearing reading of that line they were traversing. After the compass, the old transit started to come about, which would be the bottom left picture. This also, a lot of these have a compass in the bottom, so you can again take direct angle measurements. One of the bigger or bearing readings. One of the other things, they actually had a better telescope with crosshairs that you could start actually getting a better line of sight than just through those veins on the compass. Now with this could turn and measure horizontal and vertical angles. This was getting fairly modern. With the tape, with the compass and the theodolite, you were required to pull your distances. So with the compass, they used the chain like we used in the horizontal lab. As the transit started coming around, you were able to measure angles a little more precisely. Probably still used the chain, but that's when about the time the steel tape started coming about. Getting into modern instruments, we talk about total stations, which electronically measure angles and can shoot distances and elevations. That's called the EDM, the electronic distance measurement. What I got here is a picture of what we have here at school, the Trimble S5 robotic total station. I like how in the book it says a microprocessor and data storage. Data collectors, we use data collectors. Here's a picture of what we also have here at school is the Trimble TSC5 data collector. So with those advancements, with the robotic total stations data collector, they automate measurements and can perform calculations instantly. I would also like to supplement, I'm just kind of going through chapters 8, chapter 9 here, but I don't want this to replace reading chapters 8 and 9. Maybe just as a supplement, kind of going over some things. So total stations automatically measure horizontal angles, vertical angles, and slope distances. Those diagrams might be a little small. Is that kind of sort of semi-readable? But can we kind of make that out, what we got going on here? For what it's worth, the instrument's always going to be set at the vertex of two lines, the angle point between two lines. We're looking back here, the BS back sight is our initial starting line, our starting orientation. We measure to the foresight, which is the FS, measuring a horizontal angle. These instruments also measure angles to the right, clockwise. Yeah. I don't know, maybe being like the left-handed person, that always still kind of messed me up. Left-handed, clockwise, counterclockwise, which way's which? From these measurements that the robots do, the total stations, they then calculate the horizontal distance, the elevation, and you can also calculate coordinates instantly. So with the vertical angles, there's a difference between a vertical angle and a zenith angle. I think we might have talked about that early on in the beginning, close to the beginning of the semester. Your zenith angle essentially starts straight up and then measures down. Your a vertical angle typically would be from your horizon and measured up or down, would be a positive or negative. The zenith angle is going to be a constant positive, I guess, or be the right way to say that. Does that make sense? Horizontal angles, vertical angles. So with that horizontal angle, you have to have your like your back sight, your magnitude. I think one of the what we say in like one of the first sections, angular distance. I don't like that term, but I guess what it mentioned. Did I get too fast? Okay. Major components of a total station. You have your telescope, the built-in EDM, angular measurement system, the microprocessor and software. Again, that's kind of what was in this thing. It's think data collector. I need to just change that and make it say data collector. I don't like that. These systems work together to produce survey measurements and coordinate calculations. I'm sure that's probably impossible to read all of the text around that. So I pulled this off of Trimble's website again, since we have a S5 robotic total station, talking about the components of the total station. Yeah, that's not really readable back here, is it? I'll put the slides on Brightspace so you can see. Highly recommend. It's riveting, right? I mean, this is way better than my normal PowerPoints. Most everybody's still awake, and most everybody's actually even looking up. All right. I don't think we really need to get into this too terrible much. Some of the basic features, obviously, you can tell what a handle is. Eyepiece, this is for the scope where you're sighting through. You do have some knobs on the side which have to do with your vertical, horizontal turning, and the zoom, or not zoom. What am I thinking of? Focus. We have these little course sights up on top and bottom here. I kind of think if anybody is familiar with guns or shooting, on top of a barrel you have iron sights. Think of that little black box up on top there as like an iron sight. You can kind of use that to roughly sight, get yourself locked in kind of close. Then you can look through the instrument, the eyepiece, and fine tune where you're looking at on your target. These do have an extra piece where you can put an actual like faceplate on them and be able to do a little bit of manual input. We don't really ever use those. All your input's going to be through a data collector. Real nice thing with these, we saw with the distance measurement, we set this is one of what we had set up. So it has that track light. You can see the red and green depending on which side you're on. These are just a few of the functions of the S5 specifically, what we're going to use in class. They have an older Leica or something or Topcon in the book. You're still going to have your eyepiece. You're still going to have the scope. You're still going to have the rough sights, handles. All that stuff's going to pretty much still be the same. So as far as the axis on the instrument, there are 3 critical geometric axes: your vertical axis, your horizontal axis, and your line of sight. So the vertical axis would be going straight up and down. Rotating around that vertical axis is where you're measuring your horizontal angles from. The horizontal angle, think of the horizontal axis, think of your scope. You're going to turn up and down from that, measuring your vertical angles. Proper alignment of these axes are critical for accuracy. Accuracy. We like accuracy. Functions of the total station computers, the data collectors themselves. You have a handful of things that this does automatically. So in the past, we've used some old theodolites in this class. I'm starting to get these S5s integrated into this class more. What we're going to have is the data collector and actually see the readout of the angles we turn and distance we turn from the data collector. With this, you can take multiple measurements of your horizontal angles, your vertical angles, distances, things to that, like that. You input your instrument corrections, so temperature and pressure are important atmospheric conditions. We talked briefly in the horizontal distance lab, like the steel tape, you have calculations for sag and temperature and things of that nature. The temperature has to do with the coefficient of steel's expansion and temperature. It can expand, contract, depending on how warm or cold it is from the standard. That also has, those kind of things also have an effect with the laser that these instruments shoot out. I don't know if anybody's taken, I remember like when I took it was Physics 3, which was a lot of light, looking at refraction, reflection, and how different mediums go through other different mediums, laser bending through air, water, prisms differently. So having that sort of computations and corrections are important to know. You get all that stuff straight from your weather app easily. We can calculate all kinds of things. We can calculate coordinates. We can calculate our triangles. We can calculate elevations and do many different types of stakeout calculations. For those of you that will take construction staking, you'll see this firsthand in the labs where we start doing some calculations. We do a lot of stuff kind of old school by hand in the lab. Then I give you a little bit of information in the data collector, and you have the data collector do all the calculations for you. It's really cool. Greatly reduces manual field calculations. I am a big proponent of knowing your math, knowing how to calculate triangles, how to see the triangles, how to calculate things you need to. So I do like to have you do some of the stuff by hand and then see how the data collector will actually provide those calcs for you. Again, if you are going to become a licensed surveyor, that is your goal. When you take your tests, you're going to need to know some of this math anyway. So why not start beating it into your heads early? Yeah, besides greatly reducing manual field calculations, it's also a lot more efficient, speed you up. You have a less chance of errors of doing some longhand calculations. I pulled this off of Trimble's site for the TSC5 data collector, which we have here at school and we use. A lot of this stuff isn't too terribly important to what we have going on here, but we're looking at things like the screen, the power button. The TSC5 specifically, the operating system is an Android operating system. So if you have an Android phone, it probably, at least how you would maneuver inside of the data collector, would look familiar. It does have, once you open up the surveying software, that's kind of irrelevant. The operating system is more like, your computer, how you got Windows. They used to run on Windows a long time ago. It was a little iffy at best sometimes how well it worked. So yeah, you have some really nice options with that. If you like to touch the screen, it has a touch screen so you can manually go around, pick things on the screen. You obviously have your keyboard. They are set up differently. Some are alphanumeric, or like the letters are in alphabetical order. And some are that, was it QWERTY? Where all the letters are set up like a keyboard, regular standard keyboard. So it's really weird. You know the alphabet, you can do your alphabet. But when you look at that, sometimes it's like really hard. Like, where's an F? Where's a G? Where, it takes you a minute. Where like the keyboard, to me, it seems like it's a little easier to get around and type stuff out. That's just the way my head works. So, yeah, there's not a whole lot that we really need to particularly pay attention to or worry about, other than, hey, here's how it's laid out if you're really interested. Again, these will be on the right space.
It looks like a printer and a meter.
A who and a what?
A printer and a meter. The print labels.
Oh no, there's
functions F1, 3, 4, all those.
So the function keys there are a couple different things. They like in your calculator, how you have like a second function if you want to take the cosine or inverse cosine. You like second function cosine to get the arc cos or inverse cosine. That's what a lot of those function keys do, as well as shortcuts. You can set up some of these various function keys to initiate shortcuts, take you right to a specific command that you may use all the time.
So what's the difference?
But there's no printer on that, I can tell you that.
But they all got that TS something.
No, well, that's just the ones that we have here at school.
Okay.
There are other models. Depending on what companies you work for, you may have a Carlson or Leica or Topcon. I can't really speak to those. I never used them. I'm sure they all work pretty much the same way.
That's what I wanted to hear. So they probably want to do.
Just
so it's just like a meter or a printer, but it has the data of land survey.
Yes.
They look the same.
You'll have all the information in there to perform survey tasks, as well as do various calculations and things. And this is what will run your total station. This same data collector also runs the GNSS equipment, which we use in later classes as well. This data collector pretty much runs everything in our Trimble surveying world environment, whether it's the GPS or the total stations. So with telescope and sighting, the telescope allows the surveyor to precisely sight a target. You have your crosshairs, the eyepiece focus, the objective lens, the optical alignment. Proper focusing eliminates parallax error. I think we've mentioned this before earlier too. Parallax is when you're, well, I think that's actually in another, another slide. I've just pulled this out here. This is really interesting to see, and I didn't realize this when I was out in the field, like first starting out and first using these robots. When you manually turn the instrument to sight the center of the prism, you manually sight the center of the prism. Trimble has what they call auto lock, where it will automatically see and snap to the prism. And it looks like it's not snapping correctly. There's an adjustment that can be made to help minimize that offset. I do believe here it also says that it's kind of It's not a problem since the two axes have their own separate collimation data. It is, however, important to make sure the collimation test for both axes. So it kind of knows that, hey, I'm snapping to this, but I know I'm going to be off so much this way, so much that way. If it gets off way too much, you need to do a collimation adjustment to get that minimized. But apparently, per Trimble, that's okay, not the end of the world. Parallax. So that's when the image and the crosshairs are not in the same focal plane. And what that is the target appears to move relative to the crosshairs. That obviously, if you're looking through and your head's kind of bobbing a little bit or whatever, the picture looks like it's kind of moving a little bit through your scope. That's going to be really hard to manually turn and center on your target precisely when it looks like it's moving. So with that, the first thing you want to do is take your eyepiece focus on your crosshairs. I think I've mentioned this before as well. Focus your eyes on the crosshairs. Make those nice and dark and crisp as you can. Then focus on the target, keeping your eye focused on the crosshair. That way it brings those both together in the same focal plane. And even if you're just kind of moving the tiniest bit, it will look like everything's staying in the same place. Now with these robotic total stations and having this auto lock, parallax is kind of irrelevant in that aspect if you're never going to look through an instrument. However, we still look through an instrument when we're setting it up. We're looking through the optical plumb, looking down to sight exactly over a point. Parallax can happen right there. Running level loops, looking through an automatic level, parallax can happen there. So with your robotic tow station, if you're running around doing topo, collecting data, or doing stakeout, if you got auto lock prism and you're just walking and it's following you, parallax doesn't really matter. But it does matter every place else. It's still a thing. Be aware of it. Do your best to avoid. Any questions? So the electronic angle measurement, these things are measuring angles electronically. Digital reading of circles. The resolution is somewhere typically between 1 and 5 seconds. It's kind of the most accurate or most precise of an angle you can measure is going to be within 1 second, 3 seconds, 5 seconds. I believe the ones we have here are 5-second instruments. I'd need to look and double check that. Measurements appear instantly on the instrument display. Now we talk about some distance measuring. Here's the precisions that the TSC5 is capable of. With your prism in the standard mode, you're looking at 1 to 2 millimeters plus 2 parts per million. So you have a constant, you have a scalar amount there. 1, 2 millimeters. Prism mode and your standard and tracking, your tracking goes up to 4 millimeters. So that's instantly, you're going to be off that much. The parts per million, in this case, like 2 parts per million, you take 2, divide it by 1 million, multiply it by the length you're shooting. Then add that to your, whatever your constant is there. And that is the plus or minus, if you will, of how accurately you can measure a line. Are the colors in the things looking a little better? Doing a little? Man, I'm getting fancy and high tech with this PowerPoint thing. This PowerPoint might not be a fad. This might actually stick around and be a thing, huh? Maybe. So when you set up the total station, basic setup procedure here, you set up the tripod. you attach the instrument. Looking through the optical plumb, you will get that centered over the point. At that point, I guess I should have added an extra step in there. That's where you would then step in your legs, sink the legs in so it's nice and sturdy in the ground. There's a little level bubble on the tri-brac. You do a rough leveling. That's where you just use the legs of the tripod to get that bubble roughly leveled. Readjust to make sure you're center of the point. Then you use your fine leveling. Double check your center of the point, centered over the point. Remove your parallax. And yeah, knowing that essential setup or accurate setup is essential for precise measurements. This is kind of a rough step through. Again, when we get through into the lab and actually are out setting up an instrument, I'll go through a run through of how I'd set this up and go through these steps with you. And then turn you loose to let you guys practice setting up instruments over a point, getting it as exactly over the point as you can, exactly as level as you can. Some of you have probably done this before, probably should take a couple minutes, no problem. Some of you, it's probably the first time you've ever seen this and done this, it's going to take a while, and that's fine. I do like to try to make people nervous and say part of the final exam is setting up a total station in under 3 minutes. Don't worry, you'll get nervous after the lab if it takes you a minute and you're struggling, like, oh man, this is not very easy to learn. I don't do that though. But it's fun just to watch some of the nerves. Entertainment on my part at your expense. That's all. It's fine though. Seriously, we got to learn. Everybody starts at the same spot. First time everybody's ever seen it. First time everybody done it. It takes a little bit of time to get used to, but it's not impossible. We can get through it. So leveling up the instrument ensures that the vertical axis is truly vertical. So this procedure, we have the circular bubble, little bullseye bubble, if you will. That's usually sitting on the side of the tri-brac. That's going to be used for that rough leveling. There's the plate level. When you actually set up the instrument, you do have like a level vial, if you will. That will be used for more precise, getting it leveled really precise, really good. So with that, what we do here is if you look on the tri-brac, you got 3 screws in a triangular shape. Good procedure is to line up that level bubble in line with 2 screws. What you want to do is, we call the left thumb rule. We will turn our thumbs in together or out together at the same time, same in or out. The direction your left thumb turns is the direction the level bubble will move. So if you turn your thumbs in, your left thumb is going to the right, the level bubble will move to the right. Turn both of your thumbs out, your left thumb's going out, that level bubble will move to the left. Once you get that lined up in this plane with these two, you'll turn that perpendicular, so it's 90 degrees, and you will use this 3rd screw to get this bubble leveled up. Pretty exciting. Any questions?
So you say if you go in, it goes to the right, no, the left.
When you go in,
thumbs down, no. Shit, you do it.
start like that.
Okay.
Thumbs in
Thumbs in,
or thumbs out?
thumbs in. Thumbs in, what you say after thumbs in?
Your left thumb,
What you say after left thumb?
whichever direction your left thumb's moving,
What is that device? What did you say the device is going once you turn it?
it's going to move, the bubble's going to move in that same direction.
It's going to move the same
So
direction. So
I'm turning like this. Which way is my left thumb going?
It's going straight up. You got to turn
It's
sword is going to the right.
That's the way the bubble would go. If I turn my thumbs out,
It's going to go to the left.
correct. My left thumb's moving that way, and that's the way the bubble's going to go. Then we'll turn that 90 degrees, and we'll do the exact same thing. Turn this way, my thumb will go up. That's the way the bubble will go. Back and forth. So the tri-brac too, a lot of these tri-bracs have an optical plumb built into them. The robot's actually, it's on the side. You look through, there's a little 90-degree prism that's going to shoot a line of sight straight down. That's how you're going to look to see if you are over your point. And then you see your leveling screws, which we talked about over there, bringing that all together. Pretty exciting? Yes, it is exciting. Things with the robotic tow stations, they have servo motors, automatic prism tracking, remote control operation. These are robotic. Yeah, that's kind of remote control. You actually have a joystick and you can manually turn that thing up, down, left, right. With the prism, it has that auto lock feature, which it will lock on the prism and follow it regardless where you go, as long as you stay within line of sight. They claim the benefits here are one person surveying, increased productivity, and improved safety. From many years of being out in the field myself, I think I would argue about the benefit is a one person surveying and improved safety. I do believe there is safety in numbers. It is always good to have a second person, second set of eyes with you, help you check your calculations and just in general move around. I can tell you, again, from experience going out on the construction sites and laying out curb, sidewalk, buildings by yourself is difficult because you're carrying the instrument, you're carrying the legs, you're carrying the rod, you're carrying the hammer, the stakes, you're carrying everything by yourself. I don't know. I would argue that that's not actually correct from my own personal experience. Increased productivity by far, definitely. Two-person crew with a robot on a construction site can move a lot faster. Incredibly quick. Very common in construction layout. Now, one person surveying productivity and safety wise, maybe you're doing a topo out in a farm field. You know, you're by yourself, not a lot of stuff around you. You're definitely going to increase productivity. I don't know. I have a hard time with the improved safety as well. What do they know? The relationship between angles and distances. It's kind of a good concept to understand here. Small angular errors can create large positional errors. And that really those errors really increase with the distances. As your distances get longer, those errors can increase substantially. High precision angle measurement is critical for accurate surveys. So we got a little equation. S equals R theta. So S is the arc length subtended by a distance R, and the arc of theta in radians. So how far you're maybe angular, misclosure, or angular, how far off you could be angular. Convert that angle to radians, multiply it by the length you're going. It'll tell you how far off you could be positionally. To select instruments and survey procedures necessary to achieve consistency and to evaluate the efforts of errors due to various sources. It is helpful to consider the relationship between angles and distances given, and I don't have illustrated. Oh, figure 8.8. Let's try this down here. 1 minute of arc, you can be off 3/100ths of a foot at 100 feet. That may or may not be a big deal, depending on what you're doing. You're getting into construction layout, that could potentially be a big deal. 4/100ths of a foot is close to a half inch, just a little short of a half inch, to put it in construction speak. If you're laying out columns or anchor bolts, that could potentially be a big deal. And if you're getting out, if you're 300ths of a foot at 100 feet and you're going out 200 feet, 300 feet, you're going to keep getting bigger and bigger distances. That can definitely be bad. 1 minute of arc, you're looking at 1 inch at 300 feet. So 1 inch is approximately 800ths of a foot. 1 second of arc is 1 foot at 40 miles. Okay, you know what? That don't sound too bad. Maybe 1 foot at 40 miles. We're not staking or shooting anything out 40 miles. Yeah, so that is something to keep in mind. So I was sitting here thinking to myself, okay, I'm looking at an angle. I can convert that to radians really easily in my calculator. What is that you have to do? So to convert your angle from radians is your angle times pi over 180. That will put that angle into radians. In case you're dying to know. Or you remember that? Those of you who've taken trigonometry, can you vouch that for me? Confirm, deny? Observing horizontal angles. So a typical procedure, you set up and level your instrument. You sight your back sight point. You set your back sight as 0, establishing your baseline. You turn your angle to your foresight, record that angle. Instrument set up, I'm sighting my back sight. I want my angle to read 0. Everything off of this is going to read 0. Turn to my foresight and record that angular value. Pretty much 99.99% of the time, everything you measure is going to be an angle to the right. Even if you started with this is your back sight and this was your foresight, that angle to the right would be going around clockwise. Yeah, it looks something like that one. Measurements of horizontal angles. Now here's an important thing to think of too, direct and reverse observations. So we measure angles twice, minimum of twice. We measure direct and an indirect or reverse position. A lot of times you'll see, well, with the Trimble stuff, you'll see like measuring in face 1 or face 2. When you take your initial back sight, turn your angle, looking through, we'll say that's face 1. Face 2, you would flop your scope around, flip it over 180 degrees, turn back to your back sight. Your angle should then theoretically be reading very close to 180 degrees. You would record that, turn back to your foresight. What this does is reduce systematic errors caused by instrument misalignment. The final angle is averaged from both of those observations. So you could be off just a skosh, kind of take the average to get in the middle. Kind of a compensating error thing. I was looking here to exaggerate, but to show the point. I'm looking through my crosshairs. Exaggerated. My crosshairs are not perfectly vertical. I turn and I measure my angle with these crosshairs. When I flop the scope, they're going to be the other way. I'm getting confused and I'm looking at myself in the mirror and I'm like, wait a minute, which way is which? You flop the scope around, you're going to be the other way. Trust me on this. If you read an angle somewhere here on your face 1 and then you flop your scope and you read over here face 2, they're going to be off the equal amounts. When you take the average, that should be what you should be reading if these were perfectly vertical. Compensating error. Yeah? No? Flop your scope. Flop your scope. Don't look at yourself in a mirrored position here. That messed me up. You measure your angle over here. You flop your scope. You measure your angle over here. You're going to be the same distance. So you're looking at two different angles. When you take the average, it's going to put it right in the middle. It works. Trust me, it works. Repetition method. So in Trimble Speak 2, if you're doing this because you're running a traverse, this would be called measuring rounds, where you measure one direct, flop the scope face 2, measure indirect. That would be one round. Then you start back over. You could go back to your direct, measure your angle, flop your scope, go back, indirect. That would be 2 rounds. Measuring angles repeatedly, accumulate the readings, divide the number of observations. So this reduces random errors, improves precision. And there's also, I like to say, redundancy builds confidence. We like that repeatability. Man, that's the end of the first slide already.
So measuring the angle multiple times isn't the same as what you were talking about when you were mentioning flopping the scope.
It is you're measuring that same angle multiple times. Yeah. So if you think of this, you sight your back sight, you set your 0 angle, you measure. When you flop the scope and you turn back to your back sight, you should read 180 degrees as your back sight. Because think about this, this is 0. Right behind me would be 180. So when I flop my scope and look back, I should be close to 180. Probably going to be off a few seconds, give or take. Take that recording, you turn your angle to your foresight, record that. We'll do some mathematical gymnastics and figure out what the average should be in our lab. Any questions? So the importance of measuring these angles, it gets into chapter 9, traversing. So the topics covered in this chapter are types of traverse stations, angle observation methods, which we kind of talked about, distance measurements, angular misclosure, station selection, field notes. We're not going to talk about radially traversing, and errors and common mistakes. Again, I'm trying to really update and make my presentations pop a little better. Does it? Yeah, a little bit. So hopefully we'll be able to, after this chapter, be able to define a survey traverse, identify types of traverse, describe methods for observing traverse angles, explain angular misclosure, understand common sources for error. What is a traverse? Man, that's a great question. I'm glad you asked. Thanks for asking. Everybody's dying to know. So a traverse is a series of connected lines whose lengths and directions are determined from field measurements. So we set up an instrument, establish a baseline to another known point, measure that distance, measure our angle repeatedly to our foresight, measure that distance as well. Move to that point, your foresight, and repeat the process. You sight your back sight where you just came from, turn to your new foresight, and you work into a closed polygon. Does that make sense? Traverse stations, these are the points that the measurements occur. Some of the common markers would be used as hubs, which is basically a 2 inch by 2 inch by either like a 12 or a 18-inch long wood stake. Iron pins, mag nails. The iron pin, particularly in Ohio, what is going to be most commonly used would be a piece of rebar, 5/8 inch diameter, 30 inches long. Mag nails. You've kind of sort of semi-seen a mag nail a little bit. I photocopied those and taped them to the floor for our distance. And I think they're still out there. I haven't looked, but I think
Just walked over one. I was just thinking about it. It's so funny you brought that up. So I just walked over it, looked down at it, and was like, oh, it's from the lab.
that's from really out. I want to see how long they stay there.
I know one was still there. I didn't see the one further down.
Yeah, I'll have to look next time I walk up and down that hallway. Occasionally, I like to just, for a little bit of exercise, I'll walk that hallway. I need to actually like pay attention when I walk up and down, make sure they're there. Another thing with traverse points too, and what you use is really going to be dependent on what type of work you're doing and the duration of the project. If you're setting control and running a traverse that's going to become a construction project, strongly recommend using iron pins. They're going to be the most durable, they're going to be the most permanent, last the most longest time. That's probably not even proper English. If you're doing something where you just need to set up quickly and you're only going to be there for a short amount of time, I would say a hub would probably be sufficient. If you're getting into asphalt, mag nails are going to be what's commonly used there. I've seen before, and it always kind of made me nervous. People stick mag nails in dirt. Maybe if that's for a topo and you just got to get like a couple shots really quick, I would strongly recommend against doing that. For those of you that are going to work at survey companies as well, your company is probably going to have their own standards as far as what they require you to use for control. I'd be willing to bet you a dollar most, not all, definitely would probably recommend wanting to see iron pins for control points on a traverse, especially on a job site. You may even go as far as have to dig holes and mix concrete and set a concrete monument too, depending on the project. So the angles are measured at each station between the incoming and outgoing lines. So traversing is widely used for boundary surveys, construction layout, topographic maps, control surveys, route surveying. Traversing provides relative position control between survey points. We could really go into a deep rabbit hole as far as what types of control, where you would set it in regards to a project. Again, it all varies on what are you doing. Boundary surveys, you're probably not going to be there very long. You're going to run around the property, locate the monumentation and evidence of occupation around the property lines, try to establish where they are. Probably not going to be there too terribly long. Construction sites, you're probably going to be there for months. You definitely want stuff that's going to be more durable, permanent, like the iron pins, and you're going to be very mindful of where you set those off of the job site, bringing them in, trying to keep them away from areas that are proposed to be disturbed, graded. Route surveys would be typically talking about any kind of transportation work, down corridors, roadways, things like that, railroads. I don't know how well is that seen. So you got two major types, closed loop traverse and an open traverse. On the left here, we have a closed loop traverse. So we start at some point, measure around, angles to the right, all interior angles, and we tie back in, come back into our beginning point again. Like the survey plat where we start at a point of beginning and we draw all the bearings and distances around the property. With a traverse, same way. You start at a point, you go around, draw your property, and you tie back in. An open traverse is where you maybe have two known published monuments at either side and you traverse, just kind of run angles and distances from one known point to another. The closed traverse allow for error checks. Open traverse cannot typically be checked directly other than did you hit the coordinate at the closed traverse? And if you did or did not, how do you know where your error is? A lot easier, a lot simpler to find in a closed loop traverse. Again, probably 98, 99% of the time you ever run a traverse in your life, you'll most likely be running a closed loop traverse. I feel like in this day and age too, this is kind of starting to get a little dated because so many people use GPS and don't really probably pull out instruments anymore and turn angles, distances, and do traversing. It is still ultimately important and also important to realize GPS without proper checks is not a be-all end-all for everything. So again, the closed loop traverse starts and ends at its starting point, forms a closed geometric figure, allows for detection of angular and linear misclosure, and is most common in property surveys. These traverses can be many shapes, many sizes, different amount of legs to them. Here's just trying to throw a nice picture up for you guys.
Because it's not in the book.
No, I think I Googled that and screenshot it off there.
You try.
I'm trying. I just wanted a picture with some numbers on it. That's all. I wasn't looking for like anything crazy. Open traverse does not close on a known point. Common in route surveying for highways, railroads, pipelines. Since there is no real closure check, accuracy depends on careful observations. Hopefully you do have like a known point you're going to. You start at a known point, hopefully maybe have an azimuth marker or something to backsite your reference, and you start measuring, recording angles and distances down the road. I don't want to say they're like god awful and terrible and avoid them at all costs, but they're not commonly used because of lack of check. So methods of observing traverse angles. Angles in a traverse can be observed using interior angles, angles to the right, deflection angles, azimuths. The choice often depends on survey type and computations. I will also kind of just go from my personal experience of many, many years out in the field and running quite a lot of traverses. They have always been interior angles and angles to the right. I have not ever done a by deflection angle or by the azimuth. Always interior angles, always to the right. I'm not saying the way I've done it is the only way you'll ever do it. It's just that just happens to be, from my years of experience, the way it's always happened at many different companies. Interior angles are measured inside the polygon, common for boundaries, measured between a foresight backsite, and used to compute the sum of polygon angles. So when you run a polygon, actually, I'm going to jump ahead of myself here. I don't want to do that yet. Observing traverse lengths, each traverse line requires a distance measurement. Methods, EDM, the total station distance measurement. Yeah, we're using the robot. It's going to shoot distances, and we're going to get redundant measurements there. When we take a backsite, we shoot our backsite distance. When we turn our angle to our foresight, we shoot our foresight distance. Excuse me. We have done that where we measure our rounds every time we flop our scope, go to our phase 2, take our indirect measurement. When we sight our backsite indirectly, shoot a distance again, turn our foresight, shoot that distance again. And then when we go set up on our foresight and come back to that backsite where we just occupied, that's going to be a backsite where we're going to get distances measured again. This all kind of comes into play when we start doing adjustments and adjustment computations of traversing. It is important to note and realize that these things all measure slope distance. So they measure either the vertical or most likely the zenith angle, a slope distance, and it is calculating what the horizontal distance is. Now you can have it set up to display a horizontal distance immediately. Just keep in mind that it's really shooting slope distance and calculating that horizontal. Good station placement improves survey accuracy. So some important factors are clear visibility, stable ground, unobstructed sight lines, and accessibility. Clear visibility, that's like also kind of in an ideal world, you know, it's wide open, there's nothing around you, you have a clear line of sight to your foresight or backsite. You know, when you start traversing or surveying through the woods, you got to start dealing with honeysuckle and undergrowth and don't always have the clearest line of sight. It is important to try to make sure. That's why we have machetes to cut that honeysuckle and co-op students to do the machete work. I kind of joke, not really, to say like I have over 12 stitches in my body that says I'm certified to use a machete. You gotta figure out how I got those stitches. Stable ground is very important. You get into marshy areas or wet, muddy areas, you don't want stuff settling. It's always fun on a construction site when you set the gun up and all of a sudden they decide they need to run a compactor that day 10 feet away from your instrument. That's always a pain in the butt. And then so you pick up and move and then they decide, okay, I'm done with that area. I need to go over to where he's going and compact that area next. Never fails, at least for me. Unobstructed sight lines. Again, you know, you're going through the woods trying to shoot around trees and underbrush, things like that can be challenging. On construction sites, it never fails. At the end of the day, or beginning of the day, they always park all of their equipment right on your line of sight. Always have a bulldozer or dump truck or backhoe or something online. Again, that just seems to be my luck. First person out there, setting up my traverse, running it, everything's good. Construction company pulls on site, yeah, they got to park everything right around your traverse point so you can't see. Yeah, never fails.
And if you move, that's where they gotta go to.
Yep.
It's what the boss told me.
Exactly.
It's annoying. Come back to
It doesn't always happen. It just seems like.
No, it does. You know, like it does.
Stations should be referenced so they can be located later. And methods to that, just making ties to nearby objects. Pull a distance. You're doing a getting ready to develop a piece of land. You got a traverse point set close to like a fire hydrant because maybe you're using that fire hydrant for a benchmark. How far away is it to that fire hydrant? Pull a tape real quick. Okay, I'm so many feet from that, so many feet from the back of curb or something like that. Just to give you a rough idea. So, nothing will ever happen and that won't ever get disturbed or dirt pushed over top of it, but it'd be easy to find again. Measurements to nearby objects, measurements to fixed structures, witness stakes. Maybe that's something you do too. You set your traverse point, you maybe put some little unassuming lath next to it, no ribbon. Then you go 20 feet over and you put a bunch of stakes around like you got traverse points so the construction crews know where to park all their stuff so you can stay clear. I don't know. I did pull this one right out of the book. Field notes should include the station ID, so probably going to have a point number assigned to this. The instrument height, the target height, the angles you're turning, the distances you're measuring. Nowadays, we use the data collectors, but documentation still remains essential. Data collectors, like any other bit of technology or electronic device, can, you can get something that gets a little buggy. A file can get corrupt. Your field book, you're not going to get a bug in that unless a tick is crawling on the page or something. Shouldn't get corrupt too bad. But with this, we'll kind of go over this more with the actual lab itself. I'll have like a kind of a general format of the way I'd like to see the field notes. We'll have where we measure all our angles, and over on the other side, we'll draw a rough sketch of the shape of the traverse. Again, it doesn't have to be to scale, and we're not using protractors, just to get a rough idea. Angular misclosure. Yeah, I was going to jump ahead of this like a while back. The angular misclosure for an interior angle traverse is the difference between the sum of the observed angles and the geometrically correct total for that polygon. The misclosure result from the accumulation of random errors in angle observations. So, what is the geometrically correct total for the polygon? I'm glad you asked. We have a little equation for that. The sum of the interior angles is equal to n minus 2 times 180. N is the number of sides or angles within that polygon. Don't matter if it's a 3-sided, 5-sided, 20-sided polygon, you take that number of sides or number of interior angles, subtract 2, multiply 180, and that's what the mathematical sum should be of that polygon. We go around, we actually do the measurements ourselves. We add all those up compared to what we mathematically say it should close, and that difference is going to be our angular misclosure. Make sense? Questions? So like if you think of a triangle, everybody knows the sum of the angles on a triangle should equal 180 degrees, right? I got a 3-sided traverse. 3 minus 2 is 1. 1 times 180, 180. Bam, math, it's magic, it works. So that works for any number-sided traverse, polygon. Traversing with total stations. So your modern robotic total stations, They can simultaneously measure angles and distances. They can automatically calculate coordinates. You have a digital data recording. It does significantly speed up traversing. Now, I would also say with the robotic total station, well, they claim one of the benefits is running a one-person crew. I can tell you from experience, I've run traverses by myself with a robot, and it is still time-consuming because I have to go set the instrument up. I have to set up my backside. I have to set my foresight. I have to do all those angle and distance recordings. Then I have to move the instrument up to that next foresight, reset my backside, take that old backside, and move it to my next foresight. If you have multiple people, it goes a lot smoother, a lot easier, a lot quicker. We'll work in multiple groups and we'll have somebody run a backside, somebody run a foresight, somebody run the instrument, recording the angles, and we'll rotate around as we go around the polygon. So some sources of errors could be the poor selection of stations resulting in bad sighting conditions caused by alternate sun and shadows, whether you're in the sun looking into the shadow or you're in the shadow looking at the sun. Visibility of only the rod top, so barely seeing the prism. Line of sight passing too close to the ground. Lines that are too short. We always want to try to have long back sights, short foresights. We're going to be on the back hill. There's already a traverse set up. It's just been set up for I don't know how long, but that's what we're going to use. We're going to have some shorter back sights and longer foresights. Keep in mind that could be a source of error. Line of sight passing close to an object like a vehicle, which causes a refracted line of sight, and of course, sighting into the sun. I will also mention another thing in here that's not listed, heat waves. Even looking across a cornfield, you will see heat waves. It's not just looking across a parking lot, an asphalt parking lot on a summer day. I've even noticed in heat waves in the wintertime, looking across cornfields, things. Too long of a backside can be a bad thing. Too long a line of sights can be bad. And also failure to observe angles an equal number of times, direct and reverse. So you always want to do a direct, reverse. However many times you do that going around your traverse, you want to keep that very consistent all the way around. For our lab this week, we're just going to do one direct angle observation and one indirect angle observation, then we'll move to the next point. Do one direct, one indirect. Meaning we'll flop the scope, face one, face two. All kinds of different names for the same thing. Other common mistakes in traversing could be occupying or sighting the wrong station, having an incorrect orientation, confusing angles to the right and left, mistakes in note taking, misidentification of sighted station. To kind of expand on that, some of these, incorrect orientation could be where you are occupying your point, backsighting your backside station, maybe not setting 0. Or maybe you set 0 and the instrument gets bumped. Anything like that would be an incorrect orientation. Confusing angles to the right and left. Hopefully nobody does that because we're always going to measure angles to the right, at least in this lab. Mistakes in note taking. I used to be semi-guilty of this, transposing numbers when you're writing down your angles. Be sure you're very mindful of that. That is one thing I did love about having the data collector was, when I was responsible for the only recording of that angle, and if I wrote down, transposed the number, The only way to find out if that was right or wrong would be to actually go set up and measure that angle. With the data collector, you can see what the numbers actually are. Do your best to take your time in your note taking, then read and write the angles down properly. Yeah, that was good for transposing numbers. And I worked with a friend of mine uh, who was equally as bad at transposing numbers as I was. We worked together where I would turn an angle, I'd read him the angle, and he would write it down in the book. I would read a number backwards. He would hear me, but he would write it down backwards, so he'd end up writing it down correctly. Surprisingly, we did that quite a few times. So we kind of worked out really good canceling each other out, but I would strongly recommend not doing that. All good things come to an end. Chapter 8, Chapter 9, read. There is a quiz on that. I am planning to go outside with the lab. So dress appropriately. If you don't, I don't want to hear you complaining about being cold. We're getting into the construction and surveying fields, so we're going to have to be used to being outside and all year round. Okay. Any questions? Concerns? I'll have the lab. I'm still kind of trying to fix the lab as far as it's still written per the old ways, not including the robotic tail station. So I'm still kind of tweaking a few things on that. But again, we'll be using the Trimble S5 robotic tow stations and the TSC5 data collectors. And it is going to be the most fun ever. Best lab since the survey plat lab. You guys believe me, right?